Every operation that can be performed within the data grid is encapsulated in a microservice. A data management system should be able to list all of the operations that can be performed upon a collection. This enumeration can generate a list of over 300 operations that are applied within an iRODS data grid. A microservice encapsulates each operation in an operating system independent wrapper. Thus, each microservice can be applied anywhere the data grid middleware is deployed. The ability to apply the same operation across multiple types of storage systems and multiple types of operating systems is a form of virtualization. The data grid has to provide mechanisms to translate the defined operation to the protocol required by the selected storage resource. Examples of operations for manipulating a file are shown here. Each operation has an associated microservice that performs the desired action. The microservice names start with MSI. Each microservice may have input parameters and output parameters. The microservices are invoked in a rule file by listing their name with the input and output parameters listed within parentheses. Multiple microservices can be chained together to create a workflow. See the iRODS microservice workbook for lists of input and output parameters for each microservice. The iRODS microservice workbook groups files into 12 categories. The book lists more than 300 microservices that are used to create rules. For each microservice, the input and output parameters are listed, along with an example of how to use the rule. The categories of microservices include workflow operations, such as control loops, conditional tests, string manipulation, such as create and subset, algebra operations, such as math operators, metadata access query and load, such as retrieving persistent state, resource access, used to access storage systems, collection manipulations for creation and modification of collections, file manipulations for creation and manipulation of files, rule database manipulation for resetting the rule base, administrative operations to set up users and resources, messaging to send out-of-band communications, web service invocation to access a remote web service, netcdf and HDF file manipulation to manipulate structured files. Many rules rely upon standard processes for manipulating metadata, verifying input, creating log files and reports, manipulating lists, retrieving information, and creating event information. Policy functions have been created that implement these tasks. They are stored in the rule base and can be called from any rule. The policy functions, their input and output parameters, and usage examples are given in the Policy Examples Workbook, Chapter 1. A set of 32 policy functions is listed here. Policy functions starting with check are used to verify input parameters. Policy functions starting with create are used to create an object, and policy functions starting with get are used to retrieve an object. It turns out that there is a canonical structure for a rule. The canonical structure was derived by creating 175 rules to automate a wide variety of tasks for digital libraries, archives, data centers, NSF data management plans, and for protected data. A total of 97 tasks were automated, requiring in multiple cases the creation of multiple rules. The canonical rule structure is check input values for existence using policy functions, query the metadata catalog using the select microservice, loop over the result set using the for each microservice, test a condition using the if microservice, and then execute an operation using the microservices. Version 4.2 of the iRODS data grid will support a genQuery capability for issuing complex queries to the metadata catalog. This greatly simplifies interaction with the catalog, eliminating the need to do multiple nested queries to retrieve all required information. This in turn simplifies the generic rule structure to a single query and single loop over a result set. The examples in the Policy Examples Workbook do multiple nested queries and thus appear much more complex. The components of the canonical rule structure also have standard implementations. A rule that lists all of the files that you own creates a workflow variable that stores your home collection. Star call equals $rodzone client slash home slash $username client. A query is then constructed by selecting the persistent state variables that you want to have returned, such as file data name, specifying the condition where the collection name is equal to star call, and storing the query into a second workflow variable. So the query is star q1 equals select data name where call name equals star call. This selects all file names that are located in the specified collection star call. You can then issue the query to the metadata catalog and loop over the result set with for each star R1 and star Q1. You then retrieve the star file, the file name from star R1.dataname. If star file is like .r, write output to standard out file as a rule. This extracts the file name data name from the result set R1, stores the value in the workflow variable star file, tests whether the file name is a rule by looking for the extension .r, and writes each file name to the screen. The dot operator is used to extract the data name from the formatted list returned as the query result. Note that all output returned from a query is formatted as a string. The rule is available in LifeLab Zone Home RWMore rules test-query.r. We will review each of these workflow operations in subsequent modules. Take 7 minutes and complete exercise 21. Identify which microservices should be used to replicate a file, copy a file into another iRODS collection, and rename a file. Please load your paragraph into the lifetime library in the sub-collection class INLS 624 by the end of today's class.